Hello and welcome to another video. In this problem, we're going to be working on Serialize and Deserialize BST. And so basically what you need to do is you need to be able to take a BST and you need to turn it into a string in some way for you to be able to take that string in again and make a tree out of it. So for example, tree 213, let's say, you need to store this somehow in a string, and then you need to be able to take that string and return the result. And so if you are familiar with making a tree from an in-order and a post-order traversal, you should know that you need both of those to do that. But the reason you need both of those to do that is because you're not told where null nodes are equal, or where null nodes are, I guess. So like an in-order traversal of this tree is 1, 2, 3, but you don't really know like where's the root and what's the left or to the right because you're not given where the null nodes are. But if I told you this was like a pre-order traversal and exactly where the null nodes are for a bigger tree, it would work. So let's actually take a bigger tree and let's kind of show the reason why it would work if you just write down all the null nodes. So let's just say we have some tree, like tree with a node here, say maybe 5, left 3, 7, 6, 4, 1. So we have some tree like this. And then on the right we have like 15, 17, and maybe 25. This is good enough. Okay, so what we're going to do is we are actually going to do a pre-order traversal of this tree, and we will record all of the null nodes. And you're going to see like why this works out essentially. Let's actually make this a little bit smaller. There we go. So let's do that. So we are going to write out, basically what the plan is, we're going to do a pre-order traversal and write down all of the nodes. And if the node is null, we will just have like an n, and otherwise we'll have a value. Okay. So what we're going to do is we're going to start at the top, right? So pre-order, remember, goes to the root, then it goes left, then goes right. So we're going to start at the top. This has a value, so we'll write it down at 8. Then we will go left, has a value, then we will go left, has a value, and go left, 1. And now for this 1, we need to check the left and the right, but the left and the right are both null. So we're actually going to represent those with n. So we're going to say left is null, and then recurse to the right, null. Now we come back here, and then we recurse to the right side. So we will get 4. Left and right are both null. If I have enough space here, see what happens. Okay. And then we will recurse up to 3. Then we will recurse up to 5, go to 7. So we'll have 7. Then we will recurse left to 6. 6 will have 2 null nodes, so null, null. Recurse up to 7. 7's right child is null, so we'll have null. Recurse up to 5. Recurse up to 8. Now go to the right side, so we have 15. And its left child is null, so we will have null. Kind of running a little bit low in space, maybe it's a little bit smaller. There we go. Let's get rid of this just so we have enough space. Okay. So the left child is null, then we recurse back up, then we go to the right side, so we have 17, so we did 15, now we're at 17, so 17, its left child is null, and now we go right, so the right child is 25, if I did this correctly, and then for 25, we have null and null, and finally, now we're done with 25, then we recurse, and we recurse back up, and we are done. So this is the pre-order traversal of the tree, including null nodes. So now we're actually going to take this pre-order traversal, and we're going to see if we can decode it. And then we're going to compare to what we got. So let's do that. So remember, pre-order traversal is root left, right? So we're going to go one node at a time, just keeping an index of where we're at. So here, this has to be the root because pre-order traversal. Then 5 has to be the root's left, right? Because it's root left, right? Then 3 has to be this node's left. Then 1 has to be this node's left. Then we have null nodes. So this node's left is null. And now that we check the left, now we go back and we do the right. So this node's right is null. Then we recurse back up. And now this is the right value, right? Because we did the left, so 4 has to be over here. Then we recurse back up to 5 because we're done with that node. Let's actually draw it like this. Now here is a null node. So if we, or actually I think we forgot one more thing. So for 4, its left and right are both null, right? So we actually passed these two nodes. Now we recurse up to 5 and we do its right side, so its right side is 7. And for 7, its left is 6. And its right is null. Then we recurse up to 5. We recurse up to 8. Oh, we forgot another thing again, as always. So actually, for this 7, we recurse down to make it the 6. For 6, its left and its right are both null. Then the 7's right is null. That's what happened. So essentially, if you have a node and then you have two null nodes after that, means its left and right are going to be null. So then for 7, its right is null. We recurse back up. Now we're over here. Now we have 15. So we did the left side, so we're at 15 here. Now for 15, what's its left node? Well, it's null. What's its right node? It's 17. 17. What's the left node of 17? It is null. What's its right? 25. And for 25, the left and right are both null. That's kind of how you do it. You know exactly where to go, right? You always go, you make a node, and then you get its left recursion, and then you do its right recursion. And all you have to do is when you're in the recursion, we can just have this array, and then we know exactly like what node goes here. So if we actually look at our trees now, so we have a tree here and a tree here, and you can see they are the same tree, in fact. Kind of hard to see that, but yeah. They are exactly the same tree. So essentially, all we need to do is we need to do a pre-order traversal, and for every single node, if it's null, we'll just mark an N, and if it's not null, we'll just write a letter. And this can be an array of strings, and then we can just join them on the comma. So then what it will look like is like 8, 5, 3, 1, N, and so on, right? You'll have this like big string that's separated by commas, and then when we do the deserialize, we can split it on the comma, and then we'll have this array of actual values. And that's actually pretty much it. So you can construct a tree from a pre-order or a post-order traversal if you know where the null nodes are, because then you know exactly like what goes where. But if you don't have the null nodes, then you need two sets of traversals. And so yeah, definitely, and if you're still a little bit kind of unclear on this topic, I would definitely encourage you to just like draw a tree and then write out what this would look like, or even code it up and then print the actual array and then go through the tree and figure out like, okay, this is how it matches. Because it can still be confusing if you've never seen it before. But that's essentially what we're going to do, is we're going to convert our tree into a pre-order traversal where we show the location of every null node. We will make it an array, then we'll join it on the comma to make it a string that's just value, comma, array, as compact as possible, because we have to have some kind of separator value, and then we will also have null nodes. And yeah, so let's code that up. So here we have our two functions. So we're going to make a string array, and then we will make a traverse function. And so this function is going to take a node. It will be tree node or null, and it will return void. And basically all we need to do is we need to check if the node does not exist. If it's null, then we will push an N to represent null. You can push whatever you want to represent null, and we will return. Otherwise, we need to push the value, but we need to push it as a string. Technically, I think you can push it as a number, because when you join it, it'll be converted to a string, but I'm just going to do it this way. So we're going to take the value, convert it to a string, push it, and obviously for a pre-order, you do root left, right. So now we go left, left. And it is important to get all the null values. That's why we're not checking for like non-null children. We do actually want all the null children, because we need all these ends to get the right thing. So now that we did that, we need to call traverse on the root, and we need to simply return response.join or result.join on commas, right? We're going to take all the values, join it on commas, and then in this deserialize function, we are going to get a result again, and we're going to say data.split on these commas. That way we get an array again. So we get an array, and then we also keep an index, and then all we have to do is anytime we need to make a node, we'll just check. If that node is null, then we don't need to do anything, right? Like let's say we have some node with a value 8, and then we go to its left child, and then the node we're currently on and the result is null, we'll just say return none. And if it does have a non-null value, then we'll make a tree node and we'll give it that value. So we're essentially having our result, and we're keeping track of our current index is the easiest way to do this. And then we can just make another traverse function. So we can say const traverse is a function. We don't need to take any values because we are keeping track of the index. We can just keep track of the index outside. You could pass in the index, but I think it's easier to keep track of the index outside, because then it's like when you recurse, you have to know like what index to pass, and I think it's just something that's easier to keep track of outside. So it's going to return a tree node or null, depending on what the value is. If it's n, it'll be null, and if there's a value, it'll be a tree node. So we can just say if result cur, and we don't have to worry about cur being out of bounds. As long as we did our string setup correctly, we will never have a cur being out of bounds. So if result cur equals null, then we will increment it. We don't want to increment here because we might have to check later. But if it's null, then we can return null. We can also write it in a different way, I guess, if you want. So what you could do is you could just say like this, constant value equals result cur, and then you can increment like this, which would also work. And then you could say if value equals null. So you're basically saying, give me that value, then increment the index. And this is fine. So you could write it like this if you want to. And then what you want to do is, if it's null, you want to return null. Otherwise, you make a node. So we'll say constant root or node or whatever you want. And we'll call it node, I guess. Equals new tree node. And remember that this result is a string or a string array. So you want to make it a number, right? Because the value needs to be a number. So we'll say number, and we will take that value. So we'll say value. And then you would just say node.left equals traverse. Not sure why this is this, to be honest, but it still works. So. And it doesn't really tell you the error, which is kind of annoying when you do leak code. So node.right equals traverse. So you do pre-order right, you get the node, then you go left, then you go right, and then you return the node. And that should be it. And now all we have to do is call this function. So we can return traverse, and the first time we call traverse should give us the actual root of the tree. So we can just call traverse. And let's see if we have an error. Okay. Looks like we do not. And there we go. So it's pretty efficient. So let's go through the time and space for both of these, I suppose. Okay. So for the serialize, you are basically going through the entire tree and pushing it into a result, right? So it's of n. And the reason why like an array is a little bit cleaner and making it outside is you can technically return strings and just join strings. So like, let's say you have a string representation already for like the left and right child. You could just say like, well, let's just take the node plus left plus right or something, right? As like the traversal. But the annoying thing about that is you're going to be adding one node at a time to a string. So that's not great, right? You'd rather just put everything into a result and then join the whole thing, because you don't want to have like a long string that you add one node at a time into, because that's just adding like a character to a string that's really long. So you're going to have to like remake the whole string because strings are immutable. So better to make an array. And for the space, so you do have like, as usual in a tree doesn't have to be balanced. So Worst case, it's going to be O(n), because if a tree is completely not balanced, then it's going to be O(n), right? If it's like completely right balanced or something, right, where every node only has a right child or something like that, then it would be O(n). Yeah. And then for this time, so once again, we have to do a traversal of the entire tree, including null nodes. That's O(n). It's actually technically a little bit bigger than O(n), but roughly O(n), right? Because if O(n) is like the number of non-null nodes, then you can also have null nodes, so it's a little bit bigger, but roughly the same. Okay. And then for the space, once again, well, actually, you still are recursing, right? Yeah, you still are recursing, so it's kind of the same thing. So you're not recursing through your tree nodes, but you are recursing through your array, and you can have the same thing where like every node has right nodes or something. So then your recursive call stack would be the same situation. So that's O(n) as well. And yeah, so if you haven't seen this kind of way to turn a tree into a string or a string into a tree, pretty straightforward. Just keep track of null nodes, and yeah, I would definitely draw out some trees and then draw out like what a null representation of it would look like. Pick some traversal and then draw out the representation, and then see if you can go from the representation to the tree as well, and if you get the same thing and so on. It's not too bad. And yeah, if you did like this video, please like it, and please subscribe to the channel, and I will see you in the next one. Thanks for watching.